Good morning, and welcome to the last day of this excellent Congress. We start the day with three late-breaking news. The first one will be dealing with Rosetta. The Rosetta mission is a mission where there will be a lander soon, and I guess the description will be provided by the speakers today. The speakers today are Andrea Accomazzo. He's from ISA, and he's the flight director for the Rosetta mission. And Dr. Stefan Olamek. He's from DLR, and he's the project manager for the lander for the Rosetta mission. So one of the other things I want to say is, as you know, we had two late-breaking news before, and we have introduced the third one about India's Mars mission, so that will be the second topic. So with that, Mr. Olamek, okay.
Thank you very much, and good morning, everybody. I'm giving you a couple of news about Rosetta. I think it's the fourth talk that is given this week on Rosetta, so it's sometimes difficult to talk about different things, but I will try my best. We can straight go on the next slide, which is the movie we have done of the final approach phase to the comet early August this year. I would spend a long time of my life continuously watching this movie. Unfortunately, we had to go on with the mission. This is already history of space flight, if you want. For me, it was a fantastic time. These were really the last 3 days in the approach to the comet. When we got there, you see the comet moving out of the screen right now, out of the field of view. This was a sort of inaccuracy of the last maneuver we did before reaching the comet. Then we brought back the attitude, and we could track the comet directly down to the last minute. As I said, this is history. It's not the whole history of Rosetta. It's not there yet. And we couldn't stop there. It was very nice to see it, but we had to go on. So I'll give you a brief history of the navigation of Rosetta. And it's also a bit the history of navigation as well. If we could look at this chart on the top, starting from the top left, is what we call landmarks, a catalog of landmarks. And it's like when human beings started going around, we started orienting ourselves by looking around at mountains, rivers, trees. Then we started drawing maps. And this is what we did with the comet. We drew a shape model, and this is our map of the comet. Then we started navigating using law of physics, so we propagated movements like when we did first navigation with aircraft. And so we had to do with Rosetta. We had to estimate the mass of Rosetta and propagate the orbits around the comet. The mass of the comet and propagate the orbit of Rosetta around the comet. We went farther as we introduced navigation-aided system for aircraft in last century. We added aided navigation for Rosetta as well. We have models of the comet that aided us, our operators, to identify landmarks and to navigate around the comet. We went farther down the stream, and we now have completed the development of the automatic navigation. This is all done on ground, but our system on ground can automatically recognize the landmarks on the surface of the comet and tell us where the spacecraft is. So I call this history of navigation because in the end, if you look at it, it's like the GPS is our ultimate navigation device. We have the CPS, the Comet Positioning System in the mission. And this is what we have implemented. In 6 weeks, we had to go through the whole history of navigation and implement it for a space mission that is flying next to a comet. So this is what we have done in the past weeks. Basically, we have learned how to fly around the comet, and we have developed all the system required to go around it, and in ultimate instance to be ready for the lander delivery later this year. So we started also looking in further details. We have to improve our performance. We want to land on the comet. We have to be extremely precise with this operation. So all what we have done so far is not completely enough to really be precise for a good landing. So we started looking into the details. This is a picture of a section of the comet we have taken a couple of weeks ago. You start seeing some details. So we stretched a bit the images to look a bit farther. Here you start seeing already some features more on the surface. So we want to see whether the lander is going to land safely. There's not much control we can do. Nevertheless, we wanted to analyze the surfaces of the comet where we are going to land. Then we further stretch the image, and we start seeing the jets coming out of the comet. And this is something we are also learning to do and to deal with right now. So we further stretch the images, and we see also the structures in the jets. And why are we doing this? We are developing a coma model. The coma is the environment of gases and dust that is around the comet, and we want to develop an engineering model. We are in the process of developing this. This will aid significantly our navigation process, will help us in determining more accurately where the spacecraft was. We are pretty good in this, but most importantly, will help us in predicting where the spacecraft will be at a certain time in the future. And this is a fundamental element in the navigation process. We're refining these engineering models to be more and more precise in approaching the lander delivery. So we have selected a landing site. Stefan Ulamek will give you a bit more details on the details of the lander itself, what the lander is going to do. Here you have a couple of pictures taken in the past 2 days of the landing site. The landing site is on this slope next to a crater on the small lobe of the comet. Here you see from a different angle that we haven't seen so far. You see the terrain is not ideal for a landing, but there's no ideal terrain on the comet, so we couldn't have found a better place to land on this comet. Here you have another image. The landing site is more or less, the center of the landing site is in the center of the image, a bit shifted on the left side, so where there is a sort of triangle and there are a couple of big boulders next to it. And this is where we're going to land. So how are we preparing for this? Well, we have to merge it with operations that are already ongoing. The mission is flying around the comet. We are in orbit around the comet. Since the beginning of this week, we are orbiting the comet at 20 kilometers distance. To be precise, is 18.6 kilometers distance from the center of the comet. And we have to go down to 10 kilometers. The decision point is Monday morning next week. Yesterday morning, we had our last but one checkpoint. This was successful. The navigation accuracy was good enough to continue our path to go down to 10 kilometers. On Monday morning next week, we will decide whether we really go down to 10 kilometers. So we are merging the preparation for the lander delivery in November, mid-November, on the 12th of November, with a complex ongoing orbital pattern of Rosetta. What you see in white is what we are doing exactly right now. What you see in red here is the path, the orbital path the Rosetta spacecraft will have to follow to go to deliver the lander on the 12th of November. This is another picture you have seen from the sun. So we are flying on the Terminator plane. The Terminator plane is the plane divided day and night for people that are less familiar. And Rosetta is down on the 10 kilometers orbit on the blue line, and we would have to step back on a 30 kilometers orbit to deliver the lander. We fly part of this arc, then we come in front of the comet, so towards the sun side for a couple of hours. We shoot the lander out, so the green line that is falling down to the comet, and then we have a complex set of maneuvers we have to do with the spacecraft to guarantee visibility for the lander, with the lander for a couple of days at least. So the lander has to complete its primary first science sequence mission, and we have to maintain visibility. We have to absolutely get the data out of the lander. So it's a very complex orbital path we are dealing with. And okay, this is the timeline we are having. This is the path we are following. The last hours before the lander delivery are extremely critical. We have a lot of activities we have to do almost in real time. There's no real time for an interplanetary mission that has 30 minutes propagation delay, so the signal takes 30 minutes to get there and 30 minutes to come back, of course, so we cannot control it in real time. So we start 11 hours before is our first go-no-go. We decide whether we can design the maneuvers to deliver the lander, depending on where the spacecraft was in the last hours. So then we check whether the spacecraft and the lander are ready to go. This is done 7 hours before separation. Then we get closer to it and we do this pre-delivery maneuver. This is the maneuver that sets the spacecraft on a trajectory, on a path, and brings the spacecraft to a position and velocity and attitude to deliver the lander properly. We verify this maneuver only 30 minutes before the lander delivery. We will release the command to deliver the lander in the blind. So we will not see telemetry from the spacecraft. We'll have seen telemetry up to a few minutes before. We check everything is okay. Then the spacecraft is slewing into the attitude to deliver the lander. We shoot the command, and then visibility comes back. So we know whether the command was successful on the spacecraft only after the lander has already separated on board, if you want. And this is a bit odd situation. It's pretty time-packed, and we have to deal with it. Then the lander starts its descent, and the spacecraft has to continue its path. We have to do a maneuver, I call it here escape maneuver. We are not really escaping from the orbit. We are not in a collision course with the orbit, but we have to guarantee visibility with the lander. So the spacecraft starts flying away, and then a couple of hours later, an hour later, we will be able to point with the main spacecraft, with Rosetta, down to the lander that is descending. We will take images. It is our intention to prove that the lander descent trajectory is the right one, and only 7 hours later, the lander will touch down. So this is the operation we are preparing for, in parallel of running the mission around the comet, which is challenging enough. With this, I conclude my part, and I leave the floor to Stefan, that will give you more details on the landing itself.
Okay, good morning. So after this presentation by Andrea, I will say now a few more words on the lander side and landing site selection process. So if you can put my presentation up, please. Okay. Late breaking news. We didn't break anything between yesterday and today. So. Okay. This is just to remind you again. Probably you've seen this before, but this is an image of the spacecraft itself, of Rosetta, and you see on the image to the left also the position where the lander is on one of the panels, and from where it will be pushed away from orbit, from the trajectory, as Andrea has showed, to start its descent. All this descent will be completely ballistic later on. And if you look to the right, upper right here, you see again the dimensions of the spacecraft with these huge solar panels and solar generator, because we are very, very far away from the sun, only based on a solar generator. This is an image of the flight model of Philae during the qualification tests in 2001. Again, just to remind you how the lander looks like, and somehow like this, it may then also look when sitting on the comet. Now, a few words on the comet itself. I mean, we are cruising for 10 years. We were preparing. We were considering generic shapes. How could the comet look? Is it potato-shaped? What's the shape of a potato? Everything we considered, but we did not consider a duck. And this is an image which is not really old. It's about 2 months old. And this is also the time frame when we suddenly found out this bizarre shape of Churyumov-Gerasimenko. It's the first thought was it could be a contact binary. Now there is other theories that maybe due to the activity the nucleus is cut slowly into two. But we were very, very much surprised to have this peculiar shape. Now, after the first shock, we thought, can you also land on a duck? Yes, you can land on a duck. It just is a bit restrictive in regard to the landing sites you can choose. So from flight dynamics, it's difficult, for instance, to land in the neck or some other areas. But then we got even better images, and Andrea has shown some. I have some others right here. And it's not just the shape as such, which is challenging, but also the surface topography. So this body is very bizarre. It's very, very rough terrain. There is flat areas, but even on the flat areas, we find boulders. There is these cliffs. There is only a few crater-like structures, so it's not really crater terrain, which is an indication that the surface is very young. It's very active, so it gets renewed very recently. So we have this very, very rough terrain, and we had to find a landing place there. And very early we found out it will be, that's another image I should show. We do not just have images from the Osiris camera. We even made an image with the lander Shiva camera looking sidewards, because it's a panoramic camera system. So what you see in the front is the solar panel of Rosetta, and in the background the comet. Of course, with the wide-angle Shiva camera, it looks a bit smaller than with Osiris, but we also nicely see it already from the lander. Now, a few words on how do we land. So Andrea has shown the strategy the orbiter performs, but then what does the lander do? The lander is pushed away from the orbiter. We can in principle adjust the velocity of this, and then it falls purely ballistically. So gravity is low. It's about 100,000ths of Earth gravity, but still it's sufficient that the lander falls down to the surface. Releases in about 22 kilometers altitude. Takes about 7 hours to go down. Touchdown velocity will be in the range of 1 meter per second, so that's walking speed. At touchdown, we immediately fire 2 harpoons to anchor the lander to ground. We also have these screws in the feet you see here on the image, also for anchoring, and we have a cold gas system which will give some thrust also to press the lander to the surface. All of this because when we designed the mission, our major fear was the surface could be very hard like solid ice, porous but solid ice, and rebouncing was a fear. Now we know a little more about the comet from the images. There is an indication it's very soft and dusty material, so maybe sinking in may be a problem, but this is a bit difficult to quantify right now. Now this is a movie. I will not show you the complete one. You can download it on YouTube, but if you click it, just the first part of it. This is Rosetta. This is how the lander will be released. The velocity we've chosen for the actual scenario now is about 18 centimeter per second, so things go slowly, but still gravity is there and the lander will fall down to the surface. Soon after separation, the landing gear will be deployed. Well, it takes 7 hours. You have time, right? Okay, the landing gear is pushed out, is deployed. And then we also already start with some science investigations. We have a camera which is looking downward, so we will see the landing spot with increasing resolution. We are also operating other instruments like the magnetometer, like the radar tomographer. Now the selection, what were the criteria to find a good landing site there? For the site itself, obviously it's the topography, but it's also relevant the illumination, because after the first measurements immediately after landing, we are relying on a solar generator, so we need a nice and sunny place in the summer hemisphere. We also considered the boulder statistics. We also considered the slope statistics. I mean, what's the rate of slopes within the landing area? From flight dynamics, it was relevant to find a spot where the descent doesn't take too long, still not violating any of the orbiter requirements. And also for science operations, despite the fact that there is no boring place on the comet, we were of course considering what's scientific relevant, and we have one instrument, a radar tomographer, which sends radio waves through the comet, so that there were some geometrical constraints to do this tomography measurement in a good way. And after considering this, we came with these kind of generic maps. So this is an early shape model we had, and what you see to the left, these green dots, these are the areas where we could land in principle from a flight dynamics point of view. So on the head of the duck, if you wish, and on the wing, not in the neck, not in some other areas. And what you see to the right is the illumination map. Whatever is red here is permanently illuminated, like summer pole. What's blue is never illuminated, and yellow is somewhere in between. And as I said, we want due to this operation with solar generator an area where we have more day than night per rotation period. And then we came up, and that was only in August, so it's not long ago, with 5 potential landing sites, A, B, C, I, and J, not very original, but these were the naming there we had. And we investigated even further those 5 sites. Some of them turned out to be not so good, not as good as we thought originally after we looked at the higher resolution images, or we did more, or ARMOC did more refined mission analysis work. Well, you've seen this picture before. If you click it, please, it will start moving. So this is again a DTM, a digital terrain model with the color-coded illumination, and you see also our nominal landing site with name J. On the head, a relatively flat area, not too rough area, well illuminated, and good to be reached with the scenario I've described. We are still keeping a backup landing site, which is site C, which is just now in the picture. It would be better illuminated. There is some advantages also from boulder statistics, but it's more difficult to reach, and we would only go back to see if something horrible happens with J, like a sudden outburst, or I don't know what could happen. The confirmation of the landing site, as Andrea has said, will take place Sunday in 1 week, we confirm the landing site, and most probably it will be a confirmation of our nominal site C. This is now images, you've seen it before, of J, and what you see is there is flat terrain, yes, but there is also rough terrain. Another image with different illumination. It looks a bit like a terrace-like structure. Terraces are not so bad unless you're unlucky enough just to hit the cliff, otherwise we can land on all these flat areas. If you click this, it starts moving. This is again a digital terrain model of our landing site, and this reflects more or less our landing uncertainty. So this is the area we target for, and as you see, there is flat areas, but there is also cliffs, there is rough areas. And if the slope is too high, the lander can of course tumble over and will not be able to land. We've done in the selection process the analysis, I said slope analysis. We also did similar things with illumination, with boulder statistics, just to give you one example. So here you see again landing site J, and everything which is blue has low slope, which is getting green. The slope is in the 30-degree range. That's when it starts getting problematic for the lander. And what you see here in red, that's 45 up to 60 degrees slope. That causes a real problem. So you see, we have it's not 100% of the area really good for the landing. It will be risky. And it's just one slide what happens after the landing, after we've done it. As said, some signs already during descent. Then we start the first signs sequence based on a primary battery lasting about 2.5 days. Based on a primary battery means it also will work if we are in a shady valley or land in a hole or whatever would happen. Each of the instruments can work at least once. After this, we start long-term science. This means relying on the solar generator, recharge a secondary battery. This would typically take 2, 3, maybe 4 days, and then we can do another experimental run. Then we have to wait for another couple of days to recharge the battery. This phase, if we are really lucky, would last for several months until overheating becomes a problem. It may also be that there is so much dust falling back on the surface of the comet and also on the surface of the solar generator that there is no power available anymore, and this would also stop operations. That's my last view graph, and if you click it, please, it would also start. This is how you see the landing sequence from the lander point of view. So the lander is in the middle of the picture. The orbiter is now relative to the lander moving away, and you see the approach to the comet, to the landing site. And again, the real sequence is about 7 hours. We even have the landing ellipse here on this model. Until we really touch down. Yeah, and you see not even in the animation it's easy to hit the target point site. So. Okay, that was my last view graph. Keep the fingers crossed, stay tuned, be with us on the 12th of November, and hopefully everything works as nice as I have shown it right here. Thank you.
We do not have much time, but we'll just take one question if somebody has any. Okay.
If you'd seen those high-resolution images of that comet before you did the launch, would you have still chosen that comet?
Okay, I don't know if everyone heard the question. Maybe you can repeat the question.
If we had known this kind of comet before launch, whether we would have selected to go to this comet. My personal answer would be yes. I don't think there's an object as so fantastic in the solar system, and it's the best object we could select to explore because it's so cryptic, even to understand what is in there. That is a challenge for all of us, and I would select the same. I don't know whether Stefan is of the same opinion, but
well, it's certainly. I mean, it looks frightening if you have to land there. Agreed, but otherwise we are very, very lucky we have such an interesting body. I mean, it's this bizarre shape, it's this features we see there already, so scientifically, it's extremely interesting. Now, whether we possibly would have adapted the lander a bit differently, knowing it's that rough terrain, that's a different story. But it's certainly a very, very interesting body, and it's beyond our expectations, so it's great. I think I would choose it again.
Okay. Thank you. And our next talk is about India's Mars mission. The lecture will be given by Mr. Koteshwar Rao. He is the Scientific Secretary of ISRO, and he was previously Director of the Lab for Electro-Optical Systems at ISRO, and also Director of Semiconductor Lab at ISRO. He will be presenting about the recent entry of India's mission to Mars. Mr. Koteshwar Rao.
Good morning, ladies and gentlemen. In the last few days, you heard about Indian Mars orbiter mission, which has already created sensation across the globe. Today, I thought I will tell some aspects of this mission. The news is this: the Indian orbiter, Mars orbiter mission is successfully inserted into the Martian orbit on September 24th, that is more than a week ago. Just to start with, ISRO has instituted a study team to explore the possibility of sending an orbiter to the Mars in the year 2010. Of course, the boundary conditions are set that they have to utilize the available resources at ISRO, which means that they have to use the Indian Polar Satellite Launch Vehicle, which has got a limited capability of sending approximately 1450 kgs of a spacecraft. And we opted for that because it has a long history of 25 successful flight at that time. And with the study, what they have come out is, yes, initially we were thinking whether it should be a flyby. Then the study indicated that no, we can have an orbit around the Mars, an elliptical orbit, using PSLV. So this is a starting point. And all of you may remember the Honorable Prime Minister of India announced this project on the day of Independence Day in 2012. And within 14 months, we were successfully able to launch this Mars orbiter spacecraft using a PSLV launch vehicle. And the difficulty is that this mission called for a large argument of Parisi, which we have not done so far with the PSLV launch vehicle. So we had to have a long coasting phase between the third stage and the fourth stage of the launch vehicle during that time. And we also had to deploy to shipborne terminal to trace the trajectory. Finally, PSLV C-25 launched the Mars orbiter into an elliptical orbit around the Earth with 250 kilometer Parisi and roughly 23,500 kilometer of apogee. That was on 5th November 2013. That is where the journey started for the Mars orbiter mission. And we were not having enough power in the PSLV to directly set the Mars on the path from Earth to Mars. So in the process, we used the spacecraft propellant and a 440 Newton liquid engine, which was on the spacecraft, to go around Earth and raise the apogee in the process, we had 6 orbit raising operations, finally taking the apogee to almost 0.2 million kilometers. And these were conducted in several days, spanning from 7th November 2013 to 16th November 2014. And finally, we have taken trans-Mars injection at the end on November 30th local global time and December 1st Indian time. And of course, we crossed the sphere of influence of Earth within 2 days. And then we have traveled in the heliocentric path by almost 666 million kilometers, spanning over 300 days. And in the meanwhile, we had 3 trajectory maneuver corrections. One was on December 11, 2013, and second one in June 11, 2014. And the third opportunity, interestingly, we have used it for testing our 440 Newton liquid engine, which was almost at rest for 300 days after the trans-Mars injection. So we fired that engine for 4 seconds, 2 days before the Mars insertion, that is on 22nd of September 2014. And in the process, we could successfully reignite the 440 Newton engine, tested it, and also that opportunity we used it for the third trajectory maneuver correction. And it is a history now that it was successfully inserted into an orbit on September 24th, 2014. And meanwhile, all the earthbound orbits we have used for checking all the redundant systems, their combinations, and the autonomy which we have built into the system, including fault detection, isolation, and reconfiguration. That gave us an opportunity to test all the systems before we could set our path to the Mars and finally insert into the Mars. Not only that, during the earthbound observations, all the scientific payloads, we had 5 scientific payloads, all of them we could switch on. And of course, a color camera which was meant to take the pictures of Mars, we could take the images from Earth also. And all the instruments were calibrated in the process and set ready for operation when we reached the Mars. And successful insertion meant hitting the bullseye almost. We have captured the required elliptical orbit with a periapsis of almost 429 kilometers, which we targeted almost 433 kilometers. And an apoapsis, the target was almost 80,000 kilometers, and we have hit with 76,877 kilometers, and with an inclination of approximately 150 degrees, and with an orbital period of 72 hours and 43 minutes. And ladies and gentlemen, immediately after inserting the Mars into the orbit, Mars orbiter mission into the orbit, within half an hour, we could take the snaps of Mars. And this is one of the images almost with 300 meter resolution. This is the first picture from the Mars orbiter color camera. And successively, this is the first snap, and successively the 5th snap when it was going out almost, you can see the edge between the Mars and the space. And after 2 days, when we are almost near the apogee, further off, we took the image of the Mars. That gives the full disk image. And during the first orbit and almost half of the second orbit now, all the scientific instruments we have switched on, and the health is normal, and we are hoping to calibrate them in the coming few days. And also we have a plan to utilize them for the observation of the comet 2013A Siding Spring, which is likely to come nearer to the Mars on October 19th. Of course, let me also tell a happy news at this stage. With NASA, we are having a joint working group now working on Mars, bringing the strength of MAVEN and the Mars together, and probably we may have joint observations of the comet also. That's all what I would like to say. And let me conclude by saying ISRO and India have achieved an incredible mission within a span of incredible time, not to mention the very low cost which is talked about. Thank you very much.
Again, we probably have time for one or two questions, so if anyone has. Okay. Yes. What is the expected mission lifetime?
We have a leftover fuel of 40 kgs in the mission. And as per our expectations, it should be anywhere between 6 months to 1 year. And if the observations are not so adverse, it can go beyond also.
Any other question? Yes, please. Repeat the question.
Can you please be a little louder?
Yes. In addition to the comet, do you anticipate coordinated observations?
After the comet, we'll concentrate on the Mars. Just to describe you, apart from the color camera, we have 4 other instruments. One is a methane sensor, and another one is a Lyman alpha photometer, which measures the deuterium-hydrogen ratio. And the other one is a neutron composition analyzer in the Mars atmosphere. And using these instruments, after the comet, we will concentrate on the Mars atmosphere and surface.
Thank you very much. And here is again a token of our appreciation. You can always use it for strength training as well. Thank you. And the last talk this morning will be given by Dr. John David Bartow, who is an ex-astronaut, and he's also a member of the executive committee of the Association of Space Explorers. And he'll be presenting on a CubeSat project for students, so he'll be describing it in details.
Good morning. This is a little bit of an unusual presentation. I think the first time we've done an educational project in a late-breaking news, but it has some interesting technical aspects that I think you're all going to enjoy. Let me start by telling you who the Association of Space Explorers is. We are the folks who have orbited the Earth, and there are about 400 of us in this organization from 36 different countries. And you can see our mission statement here, and today this project concentrates on the fact that we are trying to use our unique perspective of the world to inspire and educate our next generation. Now, you've all probably played with a remote car when you were a kid, but you probably didn't have the opportunity to play with a remote satellite in orbit. And that is the opportunity that we're offering here, and we hope that it will stimulate the students to pursue STEM careers, and that is really our emphasis here. This project's been developed by 4 organizations. ASC has developed this challenge program itself, and it's pointed toward high school age students. It could be done for college students as well, but we chose high school age because to us, that is the point where you should be able to inspire people to move toward a STEM career. Northrop Grumman has provided the funding, and a company by the name of Ardusat has developed the educational materials and the CubeSat tutorials. And the company called Spire has actually developed the satellite itself, and they operate the satellite, which is presently in orbit. The challenge is for the students to propose an experiment that they would like to conduct in space using the sensors that are available to them on board the Spire CubeSats. And this proposal just opened, the opportunity just opened 3 weeks ago, and it's due by the end of this month. We will select the 15 best experiments and then basically give them a free ride to conduct their experiment on board the satellite. And they can actually, they formulate their experiment, they can actually write the software, which will be uplinked to the satellite, and then it'll be returned to them before the end of the school year so they can complete the project. Spire's launched 4 CubeSats so far, 2 of them via the HTV and then ejected by ISS, 1 on an Antares, and the most recent one was launched on a Nepper called Lemur 1. This is the one that will be used for this challenge, and Spire is launching additional satellites and presently doing a lot of work to expand their ground station. I think throughout the CubeSat community, they've realized that ground stations is a huge challenge, and they're working hard on that at this time. So Lemur 1 is a 2U CubeSat in a high polar orbit, a nadir pointing attitude. It's got a long orbit life, but the useful life is probably around 2 years due to radiation damage to the memory. But actually, this is way long enough for Spire. They are upgrading and launching satellites at a rate that's faster than new cell phones are launched. So they really don't need it to last any longer than 2 years. Now, there are a whole bunch of sensors on board that you can use for your experiment, and this is what gets your thinking going. There's a temperature sensor, an infrared thermopile, a luminosity sensor, a UV light sensor, a 3-axis magnetometer, 3-axis accelerometer, a gyroscope, and soon to be put online as a spectrometer. So I'm sure all of you in the audience can think of an experiment you would like to do in space right now using these sensors. And you're too old to apply for this challenge, but you can purchase time from Ardusat to go do your own experiment. I'm considering doing that myself, as a matter of fact. So the operation is that the students are provided a space kit, which comes with an Arduino microprocessor and the sensors that are on board the satellite. They can then assemble this and use it to develop their software or use the prepackaged software and just define some of the parameters within the software. And then this software is tested by Spire and uplinked to the satellite. And then the data is returned to them so they can complete their projects and reach their conclusions. This is what the space kit looks like. Looks like a lot of fun. This is the same equipment actually that is on board the satellite itself. And so this is a ground version of the satellite, so to speak, and you get to actually wire it together yourself and plug it into your laptop and get your software running. Now, you might wonder, how can you let a bunch of kids mess around with the software on board your satellite? And so they have thought ahead on this one. First step, of course, the students have got to get their software to work properly on their space kit. And then the next step is that it goes into the test facility at Spire, where they have the full satellite in their laboratory to be sure everything runs safely. And then the software is uploaded into what's called a sandbox on board the satellite, which means the software can, its access to the resources is quite controlled, and it cannot get into the network system and affect the actual satellite performance. So we hope to expand this project next year to more countries, depending on funding sources that we receive. And we would certainly like any of you who know any teachers or club leaders of high school students who would want to join into this project to jump on and Send us your proposal by the end of this month. Thank you very much. Any questions from the audience? Or your... I see one over here. Yes, we've received quite a few inquiries and actually some proposals, which is a little surprising since there's still more than 3 weeks to go. And of course, you know that people don't submit their proposals till the last minute anyway. So we're pretty hopeful that we'll certainly have at least 15 before the end of the month. Okay, thank you very much.
Thank you all for coming this early in the morning. This concludes our late-breaking session and the last event of the morning. Thank you all.